So along with the exponential and the logarithm function, there is another important collection of the transitive function is known as a trigonometric function. And these are a sine, cos, tangent, cotangent, cotangent, secant and cosecant functions. The elementary courses, they usually introduce the geometric basis in the terms of either triangle or unit circle. On that they will define this trigonometric functions. In this lecture, we introduce a trigonometric function in analytical manner and establish some of their basic properties. In particular, the various properties of trigonometric functions were used in an example in earlier part of the this course. So it is sufficient to define or deal with a sine function and cosine function, because using these two functions, the other four trigonometric function can be defined using this two. And our approach to deal with the sine and cosine function is similar with the approach we have did for the exponential function. So we have did the exponential functions are defined using it satisfying the condition that the derivative is itself and e of 0 is 1. The same concept, using that we will define what is sine function and cosine function in analytic manner. So this is the theorem that we will write. It says that there exists a function c from R to R and s from R to R such that, as we know that the double derivative of the cos, that here it is represented as c, is a minus cos, and the double derivative of sine function is minus sine for all x belongs to R. And the second property is c of 0 is 1 and c dash of 0 is 0 and s of 0 is 0 and s dash of 0 is 1. So as we have defined for exponential function, same kind of things is here, but it is for trigonometric function, so that's why it is having for the double derivatives. What we have did for the exponential function to prove that theorem, we have constructed a sequence of polynomials. It is 1 plus x, 1 plus x square by 2 factorial, up to so on. And then we have shown that this sequence of polynomial will converge to the function e. Here also we are doing the same technique. We will construct a sequence of polynomials, and that sequence of polynomial will converge to the function c and the function s. So that will give you the existence of the c and s, which is a sine function and cosine function. So we define a sequence Cn and Sn of continuous function as C1 of x is equal to 1 and S1 of s is x. And Sn of x and Cn of x we define using integration. That is, Sn of x is integration from 0 to x, Cn of x dx, and Cn plus 1 of x is equal to 1 minus 0 to x, Sn of x dx. If I call it this equation as 1, this one as 2, and this one as 3, and this sequence is true for every x is in R, and for every n it is in n, natural log. One can easily prove that by induction that this Sn and Cn is a sequence, they are the continuous function, and since they are continuous, it's integrable over the bounded interval. So thus this Sn and Cn are well defined. So I am just writing in one sentence all this. The function Sn and Cn are well defined as they are continuous on bounded interval. So that gives the argument, and obviously using a fundamental theorem of calculus, a first derivative of Sn dash, we'll say it is Scn of x, and Cn plus 1 dash x is minus Sn of x, and this is true for every n in n and for every x is in R. And again, by using the induction, that means if C1 is 1, if you use that one here, and you will have S1. See, using what is the value of C1 of x? It is 1. And C2 of x, if you want to compute, then you have to substitute here S1 in this equation 3. So that is 1 minus integration 0 to x S1 of x dx. But S1 of x will gives you x dx. So that if you integrate this, we'll have x square by 2 factorial. Same way, if you go further, you have to calculate S2 to calculate S3. So S1 of x, we know it is x. S2 of x, if you want to calculate, it is 0 to x. S1 of x dx. Sorry, S1 is this. So as per this, it is x. And if you want to calculate S2 of x, it is 0 to x C2 of x dx. And the integration of this one, it is 1 minus x square by 2 factorial, will be x minus x cube by 3 factorial. And if you go further, means by induction, one can easily prove that. So I can cite by induction, one can prove that Cn plus 1x is 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial up to so on, minus 1 raised to n, x raised to 2n upon 2n factorial, and Sn plus 1x, that is this, will be x minus x cube by 3 factorial, x raised to 5 by 5 factorial, up to so on, minus 1 raised to n, x power 2n plus 1 upon 2n plus 1 factorial. Check this. Okay. Now, what is our objective is to prove this Cn and Sn, they are the uniformly convergent sequences, and you have to prove that they are converged to the function C and S. That is our objective. So for that, as we have did for the exponential function, we are doing the same concept. Let us consider let A will be greater than 0 be given, and if the mode of x is less than or equal to A and the value of m greater than n greater than 2A, and using the Cauchy's criteria, we'll consider Sn of x, Sm of x minus Sn of x. You can see that Sm of x, if n is a smaller quantity and m is bigger, then the quantity is left is x power 2n upon 2n factorial plus x minus x power 2n plus 2 upon 2n plus 2 factorial up to so on, plus or minus, it depends on the value of n and m, is x power 2m minus 2 upon 2m minus 2 factorial. Now, since mode of x is less than or equal to A, and using the triangle inequality, we can say this is less than or equal to. And if I can take common out this A power 2m, because when you use mode of x is less than A, everywhere you have A power 2m, A power 2n plus 2, and all this sign, negative sign, will become positive. So then we'll take this A power 2n common out. In the denominator, it is 2n factorial is common out. What is left inside? This is 1 plus A square upon 2n plus 1 into 2n plus 2. This quantity is left. Plus the next term is A raised to 4 upon, there are 4 terms is left, 2n plus 1, 2n plus 2, 2n plus 3, 2n plus 4. Up to so on. Here it is left as 2 raised to 2m minus 2n minus 2, and in the denominator is left with 2n plus 1, 2n plus 2 up to 2m minus 2n minus 2. And as we know that 2n plus 1 is greater than n, 2n is greater than 2n. 1 upon 2n plus 1 is less than 1 upon 2n. So as if you use that one, 2n plus 1, and same concept we can write for 2n plus 2 also. So I can say this is less than or equal to A power 2n upon 2n factorial will be 1 plus A square upon 2n square. This is A power 4 upon, because there are 4 terms, it is 2n power 4. Up to so on, the last term is A upon 2n whole power 2m minus 2n minus 2. So this is the things we got. Now what will be this 2a upon 2n? As per this one, n is greater than 2a. So we can say that A, or I can say 1 is greater than 2a by n. Here actually I need a upon 2n. So that's why this is 1 by 2, 1 by 4 is greater than a upon 2n. So the value of a upon 2n, if this is satisfying, will be less than 1 by 4. So everywhere where we have a upon 2n, we'll write this is less than a upon 2n upon 2n factorial 1 plus 1 by 4 square plus 1 by 4 power 4 up to so on. This is 1 by 4 power, but I am adding one more and it is goes to infinity. So if I have add all more terms over there, then this series is of this, and this is a geometric series with a is 1 and r is 1 by 4 square, that is 1 by 16. And we know that ar square up to so on will goes to a upon 1 minus r. So as per this is equal to is power n 2n upon 2n factorial into a is 1, so it is 1 upon 1 minus 1 by 16. So hence this will gives you answer is a power 2n upon 2n factorial will be 16 by 15. And this will tends to 0 as n tends to infinity. As limit of a power 2n upon 2n factorial as n tends to infinity is 0. Because I have already give the argument for that summation x power n upon n factorial is convergent. If this series is convergent, its nth term will goes to 0. So that's why this a power 2n upon 2n factorial will be 0. So this quantity which we have, so what we have from this argument, what we can say, therefore cmx minus cnx is tends to 0 as m and n is tends to infinity. And hence what we can say by Cauchy's criteria, the sequence Cn is converged uniformly on any interval minus a to a. And since a is arbitrary, the value of a is anything, and it is uniform convergence, so it has to be converged to some function. So in particular, let us consider a function Cn of x is converged for each x in R. We define whatever the function we define as C which is R to R by C of x is equal to limit Cn of x as n tends to infinity. And this is for every x belongs to R. And since each Cn is continuous, C will be continuous, because we have learned that under the uniform convergence, the continuity is preserved. And what is Cn of 0? Since Cn of 0 is 1 for all n belongs to n, because you can see that what is Cn, the value of Cn is 1 minus x square by n factorial and so on. That is for C1. If x is 0, it will be 1. So Cn of 0 is 1 for any n. So if I apply the limit, we'll got C of 0 is also 1. Now still need to prove that the double derivative is itself, and C dash of 0 is 0. For that, before that, we have to do for uniform convergence for S. So if mode of x is less than or equal to a and m is greater than n is greater than 2a, again we will use the concept of Cauchy's criteria, that is Cmx minus Cnx, and the relation between these two is means s and s is the integration Cm of t minus Cn of t. You have this, and this is there. This is always true. Using the above equation, that is the mode of this one, that is mode of Sm of x minus Sn of x is less than or equal to 0 to x. The mode of this, because we know that mode of integration of f is less than or equal to integration of mode f, using this property of integration. We'll say this is using this, what we have proved is mode of Cm of x minus Cn of x is less than or equal to a power 2n upon 2n factorial 16 by 50. So this is a power 2n upon 2n factorial into 16 by 50 into dt. So this is nothing but the integration from 0 to x dt. That will gives me x. But mode of x we have taken, it is less than a. So this is again less than or equal to a power 2n upon 2n factorial 16 by 15 into a. And this will tends to 0 as n tends to infinity. So this Sn is converged uniformly on any interval minus a to a. So for that also we define some function. So hence what we can say is the sequence Sn converges uniformly on minus a to a. Let us define S, which is defined from R to R by S of x is equal to limit of Sn of x as n tends to infinity for every x is in R. Again, since each Sn's are continuous because they are polynomials, S is also continuous. That we can easily state. We note that, or it follows that S is continuous. Why it is continuous? Because the uniform convergence preserves the continuity. And what is Sn of 0? As we have defined the Sn in the manner that is x minus x cube by 3 factorial plus x raised to 5 by 5 factorial and so on. To put there, it is, so if you put x is equal to 0 here in this, then you will have Sn is 0. So Sn is 0, and if we apply the limit, you will have S of 0 is 0. So that gives you the things is S0 is 0. Now we need to prove the another things which we need. We note that what is Cn dash of x? That is d by dx of what is Cn? Cn we have defined is 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial up to so on, minus 1 raised to n x power 2n upon 2n factorial, 2n minus 1, 2n minus 1 factorial. To take the derivative, you will have it as x minus x cubed by 3 factorial plus so on minus 1 raised to n x power 2n. So 2n minus 2 will be there for the Sn. This is 2n minus 3 upon 2n minus 3 factorial. What is this? It is actually Snx. 2n minus 2 minus 1 minus 2. Yeah. Okay, so this is the Sn of x. Minus sign, so it is minus 1 here, minus plus. So it is a minus of Sn of x. For every n greater than 1, this is true. Since Sn is a uniformly convergent, Sn dash is also uniformly convergent. Since sequence Sn is uniformly convergent, Cn dash is uniformly convergent. So what is the term by term differentiation, and the limit function is differentiable? For that, it has to be satisfied 3 conditions. The first one is Cn is belongs to D of minus a to a, that is Cn is differentiable, that is already there because it is a polynomial, sequence of polynomial. Then Cn at some point, for example Cn at 0, we already proved that it is convergent, and Cn dash is uniformly convergent. So this Cn is actually satisfying all the condition of term by term differentiation, or I can say interchanging the sign of limit and the differentiation. It's satisfying all the condition, and that's why the limit function of this, whatever the Cn, a limit function of Cn is C, is differentiable. So by a well-known theorem, what I can say, a theorem which I have stated here, it is, I'm saying it is well-known theorem. The limit function C is differentiable on minus a2, and C dash of x will be limit Cn dash of x as n tends to infinity, but Cn dash of x we have conclude it is minus of Sn minus 1 x, but this is minus of x for all x's in minus a to a. Here you will have minus 1 because it is 2n minus 3. And in the similar argument, what we can say is, similarly, Sn dash of x is Cn of x. As Cn is differentiable, Sn is differentiable, again using the same argument as we have did, we say that S is differentiable because S is a limit of the Sn, and S dash of x we can say it is C of x for all x belongs to R. And now we have this C dash of x is S dash of x. Again you will do the differentiation of C double dash of x will gives you minus of S dash of x, but S dash of x is c of x. So that will gives me c double dash is c dash, and s double dash of x, as per this it is c dash of x, but c dash of x we have proved that it is minus of s, so that's why it is minus s of x, and this is true for every x belongs to R. And what is c dash at 0? That is minus s of 0. S of 0 is 0, and s dash of 0 is c of 0, and c of 0 is 1, and which proves the quantity that what we required, that exists a function whose double derivative is minus of that, and at the point 0 first derivative at the point 0 is 0, at point 0 it will give me 1, and so that is a function is there. Obviously the question is to define whether these functions are unique. For that I need to define some few properties of the first corollary of this result. We can state like this, that if c and s are the functions satisfies the two conditions, that is c double dash of x is equal to minus c of x, s double dash of x is minus s of x, c of 0 is 1, c dash of 0 is 0, s of 0 is 0, and s dash of 0 is 1, will have this property, that is then c dash at x is minus s of x, and s dash of x is c of x, which we already proved in this statement. You can just see that s dash is c dash of x, and c dash of x is minus s of x. That is, we have already did. And from this is actually it says that this s and c function having the derivative for all order, this function have derivative of all order. The next property is also saying that c of x square plus s of x square is 1 for all x belongs to R. That is sin square plus cos square is 1. The proof of this is very interesting. If you want to prove using this, that is, if I define a function as this function, and then I have to prove that this function is a constant function. So it is c of x square plus, so then just giving the proof for this. S of, I'm defining this function, define f of x is c of x square, s of x square for every x is in R. What is the derivative of this? So there is 2c of x into c dash of x plus 2 s of x into s dash of x. But what is c dash of x? As per this, it is minus s of x. So this will gives me 2 times minus c of x into s of x plus 2 s of x, and the derivative of s dash will gives you c of x. And so this is 0. And this is true for every x is in R. So derivative is 0 for every x. So therefore f of x is a constant. But why it is 1? Because in particular, what is f of 0? So we know it is C of 0 square plus S of 0 square. C of 0 square is 1 and S of 0 is 0, so that's why it is 1. And so your function f is 1 for all x belongs to R. And so this quantity is 2. Now the next is to prove that the C function and S function we have defined, they are unique. Okay, so that is the next objective, to prove that the function C and S satisfying C double dash of x is minus C of x, S double dash of x is S of x minus S of x, C of 0 is 1, C dash of 0 is 0, S dash of 0 is 0, and S of 0 is 0, and S dash of 0 is 1 are unique. So if there is a function defined like this, then they are unique functions. Okay, so let us try to prove this. Let C1 and C2 be a two function on R2R which satisfies this property. C double dash is the same, minus of that for all x belongs to R, and j is equal to 1 and 2. Cj of 0 is 1 and Cj dash of 0 is 0 for all j 1 and 2. Now, as we have did the same technique for the defining the uniqueness of the exponential function, we have to do the same here. Let us define d function, which is C1 minus C2. Obviously, C double dash or d double dash of x will gives you minus of d of x, because C1 double dash is minus of C1 and C2 double dash is minus of C2. Minus but common, and you will have this for every x is in R. What is d of 0? That is C1 of 0 minus C2 of 0. But C1 of 0 is 1, C2 of 0 is 1, so this is 0. So d of 0 is 1. In fact, if I can find out dk at 0, that means all the derivative of this function, that is C1k at 0 and C2k at 0. And it will give me 0 for all k is in M. So ultimately we have to use the Taylor's theorem to do this, to prove this one, to prove that d is 0 function. Let us consider x is in R and Ix is an interval with endpoint 0 and x. Since d I have C1 minus C2 and I am defining the t function, which is S1 minus S2. The S1 is actually C2 dash minus C1 dash, and they are continuous on Ix. Since this d and t are the continuous functions, they are bounded. So there exists k greater than 0 such that mode of dt is less than or equal to k and mode of t is less than or equal to k for every t it is in ix. So using the Taylor's theorem now, what we can say is d of x is d of 0. So by Taylor's theorem is x upon 1 factorial d dash at 0, d double dash at 0, x square upon 2 factorial up to so on, dn minus 1 at 0 upon n minus 1 factorial x power n minus 1 plus the remainder term, it is nth derivative of d at point Cn upon n factorial x power n. So we can say that by Taylor's theorem there exists a Cn, it is in Ix, such that we have this. But what we have note here, it is all the derivative at 0 is 0. So all the terms which we have here, all the terms are 0. So the last term is left here. What is the remainder term? That is dn at Cn upon n factorial x power n. Now the derivative of the d as the first derivative is also in terms of d and second derivative is also there. So it is depends on, so now what is we have either dn at Cn is either it is plus or minus df Cn. If it is n is an even, that means second derivative, fourth derivative, it is in terms of d. And for the odd number, it will be in terms of Tn. For example, first derivative is t of Cn, minus t of Cn, and so on. So any of this case, the mode of d of x is less than or equal to, that means this value dn of x or dn of Cn is either d of Cn or t of Cn, and t of Cn and d of Cn is less than k. So that's why any of this situation, this is k into mode of x power n upon n factorial. And this will tends to 0 as n tends to infinity, because the same argument as we have did. So hence what we can say is this d function is 0 for all x belongs to R. And therefore C1 is equal to C2. And since d is 0, and in the similar manner, a similar argument can show that if you can define S1 and S2 are the two functions which define as the given condition, then S1 is equal to S2. A similar argument can be shown in that manner. And so we can able to define. So what we have proved is actually a function which satisfies these properties, they are unique. This property means these two properties that we have here. And so we can able to define sine function and cosine function. So that is actually a definition of sine function and cosine function is this: the unique function C from R to R and S from R to R, such that C double dash of x is minus C of x and S double dash of x is minus S of x for all x belongs to R, and C of 0 is 1, C dash of 0 is 0, S of 0 is 0 and S dash of 0 is 1 are called the sine cosine first, cosine function and sine function respectively. And it is denoted by, as our usual notation, that is cos of x is equal to c of x and sine of x will be s of x. And then there are various properties of the sine function and cosine functions are there that I am giving you as a homework, or if some of you are interested to give the presentation on that, they can prepare it and make a video on it, and that is treated as your presentation. So that is some properties of this sine function. Trigonometric functions are left, but I'm giving you as an homework to do that because it's very elementary properties are there. So you can, if you are interested, you can do that.